In this section, we are going to learn about standard deviation. Standard deviation is a measure of deviation from the mean. We'll get to what exactly that means in a minute, but before we talk about the drab mathematical aspects of this notion, you should know that standard deviation is one of the most important formulae in all of statistics. Standard deviation is called volatility in the financial markets and is one of the most important single measures that traders and finance managers learn to keep in mind. It's a proxy for the value at risk, which is a crucial underpinning in the field of risk management. So, from every point of view, standard deviation is a concept that you should really and thoroughly understand. And in order to understand it, you first got to understand and internalize the formula. The idea of standard deviation is simple. It aims to sum up and measure how far away from the mean the points in a dataset are. Let's see what that translates to. Let's say we have a dataset. Let's go ahead and figure out what deviation from the mean even means. For every point in a dataset, the deviation from the mean is the difference between that point's value and the mean value. Here, for instance, let's say we have a set of numbers and the mean is marked there in red. Now, deviation from the mean is simply the difference or the distance of every point from the mean. We have represented the numbers here on a number line, and we have used that number line to express the deviations from the mean for all of the data points. At the bottom of the screen, you see the raw data points. Now, the deviation from the mean is simply that point minus the mean. Once we have calculated all such deviations, we have yet another vector, another list of numbers, exactly like the original list of numbers. This deviation from the mean represents how far the dataset varies from the mean. But it's still a dataset, it's not one number. What we really want is one number to summarize this set of deviations from the mean. And that one number would be what, for us, is the measure of the spread. The first brain dead option is to just take the average of these deviations. Unfortunately, this will not work even with the dumbest of bosses, simply because the deviations from the mean, by definition, will all sum to 0. If you were to calculate all of the deviations from the mean and if you were to add them all up, you would be left with 0. Why? Well, that's just because of the way in which the mean is defined in the first place. We won't get into the mathematical nitty-gritty, but it's actually really simple to show that this is the case. So you can try and do it with pencil and paper. So that rules out the brain dead option of just summing up all of the deviations from the mean and calculating their average. Our second option, which might be slightly more sophisticated, is to take the absolute values of the mean deviations and then calculate the average of those absolute values. What does that mean? Well, we would take all numbers which are smaller than the mean, and for those numbers, we would convert their mean deviations from negative to positive. We would just flip their signs. So this is not a bad option because it does at least make sure that variations or deviations from the mean on either side of the mean are regarded as equal. But there is a much better option, and this leads to the concept of variance. Variance is simply the sum of the squares of these mean deviations. There are a number of reasons why variance is a much better bet than using the sum of the absolute values of the mean deviation. So let's cycle through and understand some of them. The first reason is that variance is simply more sensitive than just summing the absolute values of the mean deviations. The mathematical reason for this is that variance squares the mean deviations and so is a quadratic or a higher order function. If that doesn't mean anything to you, well, forget it. Just focus on the simple example on screen now. Let's say the deviations were -2, 4 and -3, 3. If we only used the mean of the absolute values, in both of these cases, we would be left with the same measure of deviation, and that would be 3. However, if we use the variance, we would get a larger number for the first of the two sets of data. Second, variance does not rely on conditional functions. Well, what does this mean? From a computational point of view, if you needed to write code to calculate the absolute value of a function, you would effectively need to take a conditional. Whereas if you just want to calculate the variance, you just need to take the square, which is an arithmetic operation. In computational terms, it's far cheaper to do a square, that is to multiply a number by itself, than to do a condition check, i.e. check whether the number is less than 0. Reason number 3 is that the variance is actually fundamentally tied to the normal distribution. The normal distribution, which we will discuss in excruciating detail in just a little bit, is one of the most important distributions or probability distributions in all of nature. And this probability distribution can be entirely defined using only the mean and the variance. In other words, the variance plays a special role in this distribution. And that's yet another specific but important reason for relying on the variance as a measure of variance for all distributions and for all sets of data. Reason number 4 why the variance is an excellent measure, and this compares the variance with the interquartile range, is that variance is very sensitive to outliers. Remember that the interquartile range is the difference between the third and the first quartiles. In other words, it ignores the maximum and the minimum values in a set of data. This is good in some sense because it makes the interquartile range stable, but it's bad in the sense that it doesn't fully capture the level of variability or spread in a bunch of data. This is exactly analogous to the manner in which the mean is sensitive to outliers while the median is not. Variance is a very favored measure of variability or spread for this reason. For all of its advantages, the variance has one drawback. It's an excellent measure of the spread of a set of data, but it's not of the same order as the data set or the mean. What does that mean? Well, you cannot use the variance to say or to make an assertion like the data in this data set mostly varies between mean minus x and mean plus x. Why can't you say that? Well, because the variance squares the mean deviations. And that's where the standard deviation comes in. The standard deviation is simply the square root of the variance. Here on screen finally is the mathematical formula for the standard deviation. If you're not familiar with this mathematical notation, that's okay. Just hear me out. It's pretty simple. The summation or the sigma sign, that's the Greek alphabet for sigma, represents a sum. So what are we summing? Well, we are taking every data point in a data set, call that data point x. We are calculating the deviation from the mean of that data point, and the mean is the x bar, which is highlighted on screen. We then square this mean deviation and we sum up all those squares. We divide this sum by the number of points in our data set, that's the n. And lastly, we take the square root of what we just found, and this gives us the standard deviation. Let's go through that one more time step by step. Remember that x bar is the mean or the average of a set of data. We subtract this value of the mean from every point in the data. For every point x in our data set, we calculate the deviation from the mean. We then go ahead and square the deviation and sum it up, and we calculate the average of the squares of the deviations. This quantity, which is highlighted on screen now, is nothing but the variance. And once we have the variance, we simply calculate its square root, and what we get is the standard deviation. That's why this formula as a whole, which represents the square root of the variance, is the formula that you use if you need to calculate the standard deviation of a set of data. Remember, standard deviation is the square root of variance, and it's an excellent measure of the spread of a set of data. And because the standard deviation is defined so cleanly in terms of the variance, standard deviation shares all of the advantages of the variance that we just discussed. For instance, a normal distribution can be defined solely in terms of the mean and standard deviation of the dataset. This is why the standard deviation has become one of the most important and most popular formulae in all of statistics.